saw lines of an element called technetium. It's not naturally occurring. There's no stable form of technetium found anywhere. The longest lived isotope of technetium lives for about 4 million years. So what's going on with technetium is that if technetium was produced during the Big Bang, and they knew at the time that the Big Bang was billions of years, and it only lives for 4 million years, it should all have decayed away, and Paul Merrill should never see anything in his star. It makes no sense.
Welcome to another episode of My Nuclear Life. I'm Shelley Lesher. Today we are discussing something that really sparks the imagination and combines physics and astronomy, and may actually trigger an existential crisis if you think about it too long. The question, where do we come from? Not biologically, of course, but physically. That is the origin of matter. How are the elements in the universe created? Our guide today is Dr. Artemis Spyrou, an experimental nuclear astrophysicist and professor at Michigan State University. Artemis has spent her career studying nuclear reactions that take place in stellar environments using a variety of experimental techniques. She has extensively published on the topic and has recently been named a Fellow of the American Physical Society. There's this kind of really philosophical question of where do we come from? The story of the origin of the elements. Where would you begin?
So the story of the origin of the elements, I think, is linked very closely with the story of energy production in our sun and in the various stars. At least looking through the history, those two concepts were going together, and we only could make progress in understanding how the elements are formed when we figured out how the energy is produced in stars. But philosophically, I think people have always wondered, even in ancient Greece, philosophers were wondering, they didn't even know the elements as we know them now. They knew of different elements, but the question of where do we come from, I think, has been in the minds of people for a long time. But it was, I would say, from the physics point of view, it was mid-1900s. Some of the modern physics concepts have been established, and people started to wonder, okay, what is producing the energy of our sun? And there were some ideas, like the immediate thing that you would think is chemical reactions, or it's a giant bonfire, it's coal burning in the sun. So all of these ideas actually were explored, and they figured out that it's not enough to figure out the energy production, and all the evidence that we had, it was just not enough energy. So it was just an open question, and people didn't know what the answer was. And this kind of went on until we get to the early 1900s. The first breakthroughs, let's say, or the change happened with the discoveries in nuclear physics. So people started to discover radioactive isotopes, and they realized there's a lot of energy coming from the decay. It's called the decay heat. So one idea was actually, how about in the center of our sun, there's this giant radioactive source, and it's decaying all the time, and it's emitting energy. Can we calculate how much energy is released, and would that be enough to explain the energy coming from our sun? I mean, in this process, they knew that these radioactive isotopes, the natural radioactive isotopes, are heavy elements, and they just didn't see lines of actinides in the spectrum of the sun. So this was also dismissed very quickly, even though they started to go in the right direction.
How do you see elements in the sun? Because obviously you can't look at the sun and see elements. So how is it that physicists or astronomers would see what you mentioned as lines in the sun?
Yeah, so they see the light coming out of the sun, and there's particular energy that is associated with the emission coming from particular elements. So if, let's say, there's light coming in the whole spectrum, there's light coming from the sun in the whole spectrum, but if there's hydrogen inside the sun, then that hydrogen will absorb some of the energy exactly at the right wavelength, or exactly at the right energy that corresponds to hydrogen. So when we observe the light, we will see a little dip. we will see that that spot is missing. It has a little less line because it was absorbed. So people studied this kind of absorption lines from various elements in the lab, and they knew what to expect. So then when we look at the light in the sun, and nowadays we can do this with very distant stars, then you see the light coming and you see those absorption lines and you know what kind of elements are present.
Okay. So we're able to take what we know from the lab here on Earth and then that energy line from, say, hydrogen, when you then look at the sun, would be the same energy line.
Yes.
Okay.
So continue with the story.
Yep. So they thought maybe it was some heavy element, but then the absorption line wasn't in the spectrum. And obviously it's not a coal burning sun, which is an interesting theory, but okay. So what's next?
So the next step was, again, experiments happening here on Earth that gave some new hints. So it was in the 1910s, Rutherford at the Cavendish Institute, he started to not just observe the various elements or radioactivity, but he also started to study reactions. So he would shoot what we call now alpha particles. Actually, they also called them alpha particles because they didn't know what they were. So they just say, oh, let's just call this alpha, and the next one is beta, and the next one is gamma, until we figure out what they are. And even today, we keep calling them alpha, beta, and gamma. So those alphas we know today, are helium nuclei that just happen to come out of some of the radioactive decays spontaneously. So this is just what they had available at the time. It was the time before accelerators. They couldn't really do very much. They just grabbed what they could find naturally. So he would get these alpha particles and he would shoot them at different elements: carbon, nitrogen, oxygen. He would just shoot them at all of these and see what happens. So these were the first nuclear reactions, studying nuclear reactions and seeing, is there energy released? Are there new particles coming out? What's going on? So it was in 1920, there's a very nice paper by Sir Arthur Eddington, who tried to describe the energy production in the sun and tried to reject some of the theories and use some of the information, what people knew at the time, to come back and try to find an explanation. And he said it in a very nice way. He said, Sir Ernest Rutherford has recently been breaking down the atoms of oxygen and nitrogen, driving out an isotope of helium from them. And what is possible in the Cavendish laboratory may not be too difficult in the sun. So I like this description, and I like how it's the direct connection between what we're doing in the lab and immediately kind of thinking, oh, these kind of reactions that we are putting a lot of effort in doing them, but maybe naturally they could also be happening in the sun. And then at the same time, the other critical discovery that was very important to drive this thought was, it was Aston who did a lot of measurements on the mass of nuclei. So in 1920, again, early 1920, Aston measured the mass of helium-4, and the mass of hydrogen. And he found that actually helium is lighter than if you would add 4 hydrogens together. So immediately that kind of thought is, okay, so if somehow we manage to fuse those 4 hydrogens together to make helium, we are producing energy. There's more energy available than what is required to make the helium. So if this could happen in our sun, this would produce a lot of energy, and maybe this is what is happening in the sun.
Okay.
So you see how the different discoveries are important, and kind of go step by step, but you have to have this critical knowledge if you can make progress.
Right.
So the next problem comes in when, okay, you can say maybe there's hydrogen in our sun and it's fusing to make helium. But if you look at the temperature, people already studied the sun and they kind of knew what the temperature in the sun is. So that temperature was just not enough to have those 2 hydrogens fuse together. It's when 2 hydrogens try to fuse together, there's a repulsion, just electrostatic repulsion. And so you have to have enough energy to overcome that electrostatic repulsion. And the temperature in the sun just doesn't give enough of this energy to overcome that barrier. So again, a new problem, what's going on? And if we cannot solve this, then it's impossible to have hydrogen fusing in the center of sun. So the next discovery that made the difference was in 1928. That was a Russian physicist, George Gamow, who used basically the knowledge at the time of quantum mechanics and described that, sure, you have two hydrogens, they're trying to fuse, they in principle don't have enough energy, classically they don't have enough energy. But from the quantum mechanics point of view, there is a small probability that those two will fuse even at a lower energy. So this is called the tunneling effect. So it's like one of the protons is tunneling through the barrier of the other proton. And so even though the probability is small, it's still possible to have that fusion. And since in our sun there's so much hydrogen available, even a small probability is enough to get this going and produce energy.
And again, we do know it's there because we see it in the absorption lines. So somehow it has to be produced.
So we see the hydrogen, we see the helium. It's just the question was, are these used to produce energy or not?
Okay.
So this discovery from Gamow was 1928, and already 1929, so just a year later, it was two physicists, Atkinson and Houtermans, who used this discovery from Gamow, and actually they put together the whole calculations and they figured out that this is a realistic way of producing energy in our sun. So that was kind of the next step. We're still not even discussing production of elements, but we're starting to, because this is an important step. If you have in the sun, if the energy production is happening from fusing hydrogen into helium, then all of a sudden you're also making a new element. You're making helium.
Okay. Yep.
So that's why I said in the beginning the two topics are linked together, because if through nuclear reactions producing energy, you have to produce heavier elements. So maybe this is the way to make even heavier elements. It's still unknown at this point, late 1920s, it's still unknown. And it's also important that at this time, even the neutron had not been discovered yet. So we know the neutron plays an important role in this whole process, but at the time, they kind of figured out all the basics and they figured out that, it's hydrogen fusion into helium. We don't know exactly how it happens, but it's hydrogen fusion into helium that drives the energy production in the sun.
But they knew helium was bigger than hydrogen, right?
So they knew helium was bigger, but they knew that was Aston's mass measurement. They knew that if you add up 4 hydrogens, you make more energy, more mass than the mass of helium.
Okay, but they didn't know that it was 2 protons, 2 neutrons at that time.
Correct.
Okay.
That was 1920s. The neutron was discovered 1932. So it's still a few years later.
Okay, so, once then the neutron's discovered, how do things change?
So then maybe now we'll go into details, but of course now we have a more accurate picture of what happens. We know even today, but they figured it out early on, that when you get 2 hydrogens and you try to fuse them together, you make something that would be a helium-2 nucleus, just 2 protons coupled together. And that is not a bound system. So immediately, as soon as you make this, immediately it breaks apart. So you cannot really go to helium by fusing just 2 hydrogens or 3 or 4 hydrogens. You need something else to actually make it to helium. This is actually philosophically an important point, at least for me, that if it was possible that the 2 hydrogens would fuse together, make helium, and then the helium from the helium kind of move on to the heavier elements, there's just so much hydrogen in the sun that the whole process would go very quickly. Because you have so much hydrogen, if it's a possible reaction, it would just go. So maybe as soon as it would reach the right temperature, it would just fuse all of this together very quickly and maybe even explode. I don't know, but it would definitely not live for 10 billion years that our sun lives right now. So the fact that this kind of reaction is not possible, and it's another reaction that is very hard to do, it's a very rare reaction where when you fuse those 2 protons together, every once in a while, you end up with a deuteron. One of the protons is converted into a neutron. It's called a weak process. It's such a rare process. But again, if this was easier, then we would not be here to wonder about it because everything would go so fast. So there's many things in nuclear astrophysics. There are many things like this that, oh, this is such a hard reaction. Why is it so hard? But if you think about it, if it was easy, then everything would just progress so much faster.
And we wouldn't be here.
Yeah.
Wow. Okay. So you are a bit of a philosopher as well.
Not quite, but this kind of reactions it get me thinking. There's a few of these instances. It's similar with the tunneling effect I mentioned earlier. If it was not possible through tunneling, we would have to wait until the temperature in the star or in the sun goes up high enough. But it's a threshold, so as soon as it would hit that threshold, immediately all of the hydrogen would fuse. So the fact that there's tunneling and there's a small probability and it kind of goes slowly, again, this is why our sun is burning for billions of years.
So we know that more happens, like that this just gives us two elements, right? We just have hydrogen and helium. But if you look at the periodic table, there's a lot more elements there than two. So how do the rest of them happen? Like what happens in our story that we get more than this?
So at that point, there was, I would say, two major opinions about what's going on. One was George Gamow saying that all of the elements were produced during the Big Bang, and there's a static element abundance throughout the universe. They were produced during the Big Bang, they just got spread out throughout the universe, and this is what we have right now.
I think, though, a lot of people have heard of that. When you ask people, they'd be like, oh, everything was produced during the Big Bang. And I think that's a common, but that's not the only option.
Yeah, that was the one opinion. Already there was a little bit of issue here because we just discussed how hydrogen fuses into helium. So at least of all the elements, helium cannot be static because we know it's produced from hydrogen. So there was already a little bit of an issue there. So the other opinion, the other idea came from Fred Hoyle. And he proposed that the elements were not all made during the Big Bang. It's only the lightest elements that were made during the Big Bang. And all the other elements, the heavier elements, are made in stars. So Fred Hoyle was a theorist. And so he created an explanation, theoretical explanation of how this could work and so on. And this was mid-1940s when I guess a lot of the nuclear physics was starting to be known, the reactions and the neutron was there and the proton was there, the masses were known. So it could be a little bit more accurate, but these were the two competing ideas. And as usual, when the two ideas are theoretical, what you need is an experimental verification to support one or the other. And this came in 1952.
So that's not that long ago.
That's
in the grand scale of things.
That is definitely not very long ago. But you have to have, together with all the discoveries in nuclear physics, then you also had to have advanced telescopes to be able to make some of these discoveries. So the discovery that was a game changer was an observation. It was Paul Merrill at the Mount Wilson Observatory. He was making observations of different stars, and he saw something that was surprising. He saw those lines that we talked about before about the sun and so on. He saw lines of an element called technetium. Now, technetium is a special element. The word comes from the Greek word technito, which means artificial. So it's an artificial element. It means that it's not naturally occurring. There's no stable form of technetium found anywhere. The longest lived isotope of technetium lives for about 4 million years. So what's going on with technetium is that if technetium was produced during the Big Bang, and they knew at the time that the Big Bang was billions of years, so they had the time scale already. So if technetium was produced during the Big Bang and it only lives for 4 million years, it should all have decayed away, and Paul Merrill should never see anything in his star. It makes no sense. So if looking at the paper from Paul Merrill was just a report for a conference, so he said that, well, there's three explanations. One is either there is actually a stable isotope of technetium, it's just that we haven't seen it yet. The second is that this star is making the technetium as we speak, and that's why we can see it. And the other one is maybe it was made in some other star and somehow made it into my star that I'm observing. So we searched for a long time. There is no stable isotope of technetium. The technetium isotopes are as we know them, and we are still discovering new isotopes of technetium, but they're all a lot more short-lived than this one. So 4 million years is the longest one. So the answer was one of the other two, that somehow either that star or some other star was making technetium, and that's how he could see it. So this was in support of Fred Hoyle's theory that the elements are made in stars and not during the Big Bang. So this is kind of, I would say, the field of nuclear astrophysics, or the field of stellar nucleosynthesis. So the synthesis of the elements in stars, I think that was the moment that it was born, because it was the proof that, yes, this is happening.
Wow. So that's the beginning of trying to figure out how everything then is created. And so this is what you study. Why do you study this as a career?
Well, it's that curiosity. So maybe I'm a little bit of a philosopher. I don't know, but it's that curiosity of the how are we all made? And you're looking at the universe and you're studying the stars and so on, but there's a direct connection between what is produced in the stars and what we are made of. All the atoms and the nuclei in our bodies came from some stellar process somewhere. It was a few billion years ago, but still they happened there. So understanding how that worked and how they were produced in the different stellar environments. It's not all happening in one environment, it's happening in many different stars, and somehow they all have to come together to make what we are today. So this is, to me, this is just a very fascinating question. And so trying to do research and design experiments that can address this is just very interesting.
That is pretty cool to try to figure out how it all pieces together. And I'm guessing you have to work not just with nuclear physicists, but also with astronomers and astrophysicists to try to figure it out.
Yeah, so the field is multidisciplinary. From its birth, it was multidisciplinary. So Fred Hoyle, for example, could not have done this alone or describe everything alone. He had to work, even in those early days, he had to work with observers and with nuclear experimentalists to try and figure out how this works. And actually, going back to our story, that was the next step. It was that 4 people, representatives of the different fields of nuclear, subfields of nuclear astrophysics, had to come together to put together a comprehensive description of all of the different processes that make all of the elements. So that was Fred Hoyle, he was in Cambridge, and Willie Fowler, who was an experimentalist, a nuclear experimentalist, went on a sabbatical visit to visit Hoyle in Cambridge. And so the two together, this was right after the Paul Merrill discovery. So they were discussing this. And then at that time, there were 2 astronomers, a couple, Margaret Burbidge and Jeffrey Burbidge. And they invited those 2 as well. So the 4 of them were together in Cambridge, and they started to discuss and try to write a description of all of these different astrophysical processes. And they continued later on. They went to California for some time, and they just all worked together for a few years. And in 1957 was the first comprehensive description of all of the stellar processes that make the elements. And even today, this is the landmark. This is the paper that everyone refers to as the first step, the origin of stellar nucleosynthesis.
This is the famous paper, right? The synthesis of the elements in the stars.
That is the famous paper.
And it's got a nickname.
It's B2FH for the initials of the authors. And I will say that how proud I am that it was a woman first author. Out of the 4, she was the first author, Margaret Burbidge.
That's fantastic. It is something to be proud of. So what was their description? I mean, this paper has stood the test of time, right? It's from 1957. Everyone cites it. I mean, I don't know how many cites it's had, but it's thousands of citations. I give it to my students whenever they're interested in how elements are formed. It's a great paper. So what is the story that they put together on what's happening in synthesizing the elements?
Yeah, so I'll say that a lot of what they described is still true today. We still find that it was accurate, but also a lot was not so accurate because their knowledge was more limited, both on the astronomy side and on the nuclear physics side. Of course, now 60, 70 years later, we know more. But the main idea, the big picture was correct. So the way they described it is we have the protons fusing into helium and they release energy. When this is happening at the core of a star, then this kind of energy that is released, it helps to balance the gravitational collapse of the star. So as the star is trying to collapse under its own gravitational weight, then there's all of this energy produced in the center that helps to balance this. And this brings us from hydrogen to helium. It's the first step. When you run out of fuel in the center, run out of hydrogen, you just have helium. The helium now is a little bit heavier, so it cannot really react just yet. It needs a higher energy, higher temperature to react. So it's just stuck there in the core of a star. There's nothing to balance the star's gravitational collapse, so the star does actually collapse a little bit more. And this increased the temperature of the core a little bit more. So now the helium can ignite, the helium starts to fuse. And when the helium fuses, it's a special process called the triple alpha process. So 3 helium nuclei will fuse into carbon. So that's the next step. I won't go through every single step, but this is kind of the idea. At every step, you have some reaction that ignites because the temperature of the star goes a little bit higher. That nuclear reaction releases energy and it produces heavier elements. So this kind of step by step, it goes through the evolution stages of a star and it goes through the different steps of the nuclear reactions. And you keep doing that until about iron. There things change because for iron, it's a very bound nucleus, and it just happens that if you go above iron, this kind of reactions stop releasing energy anymore. We need energy to make this reaction happen. So then it doesn't help with the balance of the star, and it's just almost impossible to go from there to produce heavier elements just because it's hard and we don't have enough energy in the star. This is also a delicate point because once you run out of energy and you create this iron core and there's no other reactions that you can do, this is where the star collapses and this is where a supernova would happen, for example. So this is interesting to me how the two processes, how a star evolves, how it produces its energy is very much linked to the element production and the energy production and all of these nuclear reactions that are happening in the center of the star. In their original paper, they described all of these different processes, the kind of reactions that could be taking place and how much energy is released and balance things all the way to iron. And they even proposed mechanisms to make heavier elements above iron that cannot happen with the usual fusion reactions with the protons and the helium. For that, you need neutrons. Neutrons are neutral particles, so it's easier for a neutron to penetrate the nucleus and just have a reaction. So if you happen to have an environment, a stellar environment that has enough neutrons, then those will get captured on the existing nuclei and slowly help through these processes, slowly help to build heavier elements. So this idea of fusion reactions at the lower masses and neutron-induced reactions for the heavier masses, it's still true today. We've discovered a lot more and we understand a lot more the details and where these things can take place and how a star can produce the neutrons or whatever else is needed. But the basic ideas were already set in this original paper.
What's changed since then? So, for example, I know the LIGO announcement really pushed the field forward. How did that change this theory?
So in the original B2FH paper, they already presented that there must be 2 neutron processes that have to make the heavy elements. It has to be something called the slow neutron capture process or S process and something that is the rapid neutron capture process or R process. They couldn't explain the observed abundances. Otherwise, they needed these 2 different environments. So the S process, from the nuclear physics point of view, the nuclei involved in the S process are all stable nuclei or very close to stable nuclei, and we've been studying those for many, many decades. So the S process, I would say, is very well understood. There's still some puzzles and there's still some work done, but most part, it's well understood. The issue has been the R process because it involves nuclei that are very, very rare, very short-lived. They live for a few milliseconds. And they're also very hard to make in the lab. Actually, only now we are able to make some of these nuclei, and next generation facilities will be able to make these rare isotopes. But up until now, we're barely touching what our process nuclei are supposed to be. So because of that, there are a lot of questions related to this R process. And the R process is responsible for making half of the isotopes of the heavy elements. It's contributing a lot, and we don't know very much. So the conditions, where it takes place, there were two scenarios proposed. One was in supernovae. Supernovae are relatively common, and people expected that this is the site or where the R process is happening. And the other option was in the merging, when you have two neutron stars and they merge together. This also creates an environment where you could have the R process. But it was a debate for many years. It was, this scenario has these issues, this scenario has these issues, and we didn't know, and there were no observations. So the LIGO discovery was very important for the field, because finally what they did in 2017, they saw for the first time gravitational waves coming from the merging of two neutron stars. And then at the same time, other telescopes from all over the world turned to that direction, and they observed a light that's coming out of that. So it's not the gravitational wave that gave us the signature for the R process. It's actually the light that gave us the signature for the R process. So what we saw is basically exactly what we expected to see from an R process, which was the first confirmation that, yes, this is where it's taking place. This is at least one possible place where this R process can take place. So now you can work on figuring out the details and how does it work and how much of these elements are produced in this environment. And there are so many questions that are created, but we had to know where before we can even dive into all the details. But it was fascinating to see and just be part of that discovery, because before that, all we had as evidence for the R process and all of these heavy elements, all we had was abundances, was this light that I mentioned at the beginning, the absorption lines, and we would see at a distant star and say, oh, this star has gold. How did that gold get there? Where was it created? How long has it been there? No one knew. All we knew is that gold was produced somewhere in that neighborhood of the universe, and it made it into that star. And a few millions or billions of years later, we are observing that gold. So this is important signal, of course, but there's many steps in between.
That theory was presented in the 1957 paper? That two neutron stars would collide, that was presented as a theory?
That's a good question, and I don't remember if they specifically mentioned the two neutron stars. This was more recent, like in the last few decades. That was more recent. I don't remember if they had it in their paper or not.
But it was a theory before LIGO came on.
Oh yes, it was one of the models. But yeah, it was very exciting, because now the light that we saw, the shape of that light and how fast it was coming and the wavelengths and everything about that light corresponded to radioactive decays, these very exotic radioactive nuclei, as they are decaying slowly back to make it to stable elements. As they are decaying, they are emitting radiation. And we're directly observing that radiation. It's one-to-one. It's just the immediate information coming live from that star, those two neutron stars merging together. And so that's a very big difference compared to having just these abundances from some event millions or billions of years ago. So that's what very exciting, and so much more information for our modelers to look at, and the observers analyze the data, and the modelers now create new models to describe and reproduce the data. And of course, the nuclear physics comes in, because unless you have the accurate nuclear physics, your model is not going to work in a good way.
So do we know everything now? We know how all the elements are created and we can explain it all?
Absolutely not. It's one of those things. I would say that today we realize that we know less than 10 years ago. So up until 10 years ago, we had our observations and we had the processes. We didn't know exactly where the R process is happening, but we knew that, there must be an R process, there must be an S process. They're about 50-50 producing the heavy elements. There's this third process called the P process, producing even less. But we had the big picture, and it was very similar actually to the 1957 paper. What changed in the last decade is now with the advanced telescopes, we have a lot more observations, and we started to get observations of stars that we cannot reproduce with this scenario.
Oh,
So now
no.
we're back to the drawing board and say, wait a minute, we thought we had it all figured out and it was just kind of getting the little details. And now we have this observable that we cannot match in any way. No combination of S or R process can reproduce these new observables. So this is fascinating, and it made our modelers go back to the drawing board and come up with new ideas. And some of these ideas are not brand new. They were proposed, let's say, 30 years ago, but no one followed up on them because there was no observation to explain. We didn't need a new process. Why would we add a new process if we don't need it? And now we realize that, oh, wait a minute, we need to add something more. Something is missing. For example, my research right now focuses on one of these new processes. It's called the I process. I is for intermediate between S and R. So it's not as exotic and as fast as the R process, but it's not as stable, let's say, as the S process. So there's a lot we know already from the nuclear physics point of view, but there's also some that we don't know. So we're working on figuring out what are the contributions of this new process, where does it take place, and is it needed to explain the solar system abundances, or is the solar system already explained with SNR, and maybe this new process is only needed for some other stars? So there are a lot of questions we're trying to address.
So there's still a future in this field.
Oh, absolutely. We are definitely, as I said, as we learn, we realize how much we don't know. And it's exciting to move forward.
So, what do you see moving forward as the biggest questions that are still left unanswered, besides the I process?
Yeah, and the eye process is just a small piece of the puzzle, and there might be more, there might be other things that we don't know. I think in this field, what we learned is to be alert for new discoveries, because these are what are driving the field. So the eye process I mentioned came because there were new telescopes and they made new observations. And this is what's driving the field. We are here to explain the observations. We're not going to get new observations from the solar system. We know the abundances of the solar system for many decades, but we do get new signals from stars. We do get new signals from meteorites. There's little grains embedded inside meteorites that were created before the solar system was formed. So we get information from exotic sources that are not stars, and we still get them. We get them here, we get them in the lab, we can analyze them, and we get the signatures. We are discovering radioactive isotopes in our oceans. There was a lot of studies recently on looking for this isotope iron 60, which lives for a few million years. So it's not left over from when the solar system was formed. So if we find iron 60 on Earth, it must have come somewhere. Maybe there was a supernova nearby and it just ejected iron 60 and it made it to the Earth. So we look into our oceans and we find this radioactive isotope. So we're trying to explain, where did
Wow.
it come
Yeah.
from?
Where'd that come from?
So there's new telescopes that are being launched in the next few years, and already there was one recently, and there's more coming up in the next few years, and we expect that there will be a lot of new discoveries. So as a field, we need to be alert for these new discoveries. And then on the nuclear physics side, I said there's a lot we don't know about the R process because we didn't have access to the right nuclei. So for example, here at Michigan State, we just started the new facility, the facility for rare isotope beams, which will give us access to the majority of these R process nuclei we never had access to. So we don't know what we're going to find. That's the exciting thing, is that we have a theory, we have a prediction for what these nuclei should behave like, but unless we really go and do the experiment, we're not going to find out. And there's a direct connection between the properties of these nuclei to what you end up with in the abundances in the stars. So there's a lot of new things going on in the field that I cannot predict what the new discovery is going to be, but we are ready. And we have these collaborations working together with nuclear physicists and observers and modelers to be ready to explain and tackle these discoveries.
Thank you for listening, and a very special thanks to my friend Artemis. Please leave us a rating or review on Apple Podcast or wherever you are able. Visit us at mynuclearlife.com for more information about our podcast. Until next time, I'm Shelley Lesher, and this has been My Nuclear Life.